So now we'll take a look at problem 6.2, and we're given a specific molecule named here, and we're told that it's isolated from this certain species of plant and all these great details. But what we're interested in is the chemistry, right? So we have our first bit of information here. We're told that we have this carbon-carbon double bond, and we're told or reminded that is comprised of a sigma bond and a pi bond. So on to our table of bond dissociation energies, we're given the value for only sigma bonds. So in this example, we're given a value for both those energies combined. So this is telling us that the sigma bond dissociation energy plus the pi bond energy together, combined rather, equals the 607 kilojoules per mole. So we have that information, and then we're asked to use that and estimate the enthalpy change. So overall, whether this will be an endothermic or exothermic reaction, we can make that determination when we're done from the conversion of compound 1 into compound 2. So we're given this final compound here that's been isolated, but we're told that we're just looking at the precursor molecules here. So compound 1 and this first step of the mechanism where it's converted into compound 2. So we won't actually look at, after those two subsequent steps happen, our final product. So just keep that in mind, that we're just looking at the change between compound 1 to compound 2. So how we can approach this problem is just to kind of break down where the change occurs. So what we're going to do is we're going to call all of this an R group. So this here is an R group, and we're going to look at specifically the bond that's broken. So I have here a carbon-carbon double bond, and I know that that's connected to hydrogens, right, on both sides here. And then we have our R group down there. So that's where the change is going to occur, right, from compound 1 to compound 2. So we're going to pull this part out here and bring it down. And what else do we have reacting here? So then we also have HBr over our reaction arrow. So light hits that, activates it, and we see this portion of the molecule has been changed in this fashion. So our product will look like this. We'll have hydrogen, hydrogen, and our R group on this carbon. And now we have a single bond to the other carbon, and the other side would have the bromine and look something like this. So we have our pi bond broken here, and then this HBr bond broken. And then as far as bonds formed, we have this bond formed here and this bond formed here. So the hydrogen and the bromine both add to that double bond. So let's go back and let's look at the information that was given previously. So we were given the total amount of energy in this double bond. So let's break this down here. So we have our bond dissociation energy for the sigma bond plus the bond dissociation energy for the pi portion of the bond gives us this total 607 kilojoules per mole for our double bond. All right, so that's 607 for both sigma and pi components. So again, we're told that we have let's go to our table and we can find out how much energy is in a single bond. So we'll go back to our table. There's some notations from the last problem still here, but I'm going to look for what our sigma bond dissociation energy is. And we're going to use propane here because the substitution pattern on our alkyl component, where the substituent is attached, where the R group is attached, has the same pattern. So this energy that we can associate with just the sigma component would be 356 kilojoules. Let's find that here. Oh, here we go. So this down here tells us within our carbon-carbon bond that we're breaking, 356 kilojoules per mole is contained in the sigma portion. So that's the only information we'll need from this table. So we'll go back down here and we'll plug that amount in. So if 356 kilojoules per mole is in our carbon-carbon single bond, we can subtract 607 minus that amount, and that will be the energy in the pi component. So that would be, we have to add 251 kilojoules per mole to break that bond. So we'll put that number here. And then what's the other bond that we need to add? So this HBr bond. So let's go back to our table to see that, just for reference. So we see from a previous problem, we picked out that value here. So we have 368, the kilojoules per mole that we would have to add into our reaction to break that HBr bond. So let's add that here. All right, so overall, these are the amounts of energy that we need to add to break the bonds in red. And now we have two bonds that are forming on this side. So we have our HC bond, and then we have our CBr bond here. So let's check out those values. Again, will approximate based on these molecules over here. So something similar to propane, right? But with a bromine added. In this case, we would use this value over here, this 285. And again, we're using those values because the substitution pattern, or looking at this alkene forming this alkane, where the reaction is happening, is very similar to the pattern of the propane that we see, where a double bond is broken, and then in our case, a bromine is added. So that's why we're using that 285 value here. And we can use, again, from the table, 397. I'll show you where that's located. Over here for the formation of a CH bond. So that's over here where I'm circling. All right, so let's go back and we can find the difference between these two values. So we would add together 251 plus 368, and then we would subtract the 397 and the 285. And overall, we would see that this equates to negative 63 kilojoules per mole. And we know that a negative enthalpy change, right? This is our delta H. This would tell us that this is an exothermic reaction. All right, so we will continue next time with practice problem number 3 from chapter 6.